So to start off this video, we're going to find the area under the cosine curve from 0 to b. So we will have the integral from 0 to b of cos x dx. We'll take our antiderivative of cos, which is sine. So we'll have sine x, and we'll evaluate it from 0 to b. So therefore, we're going to get sine b minus sine 0. Sine of 0 is 0, so really we just get sine b. So if we look at a picture of what that's really representing, so that's saying our area under the curve for cosine will essentially, from as long as we're going 0 to pi over 2, is just sine of that value. So if we want it all the way up to pi over 2, sine of pi over 2 is really just 1, which is kind of an interesting fact that from 0 to pi over 2 there for cosine, that area underneath is really just 1. So review of our two fundamental theorems of calculus, both parts. The first part, if you're taking an integral of some function, and then you take the derivative of it, essentially you just end up right back at the beginning. So imagine if we had the integral 0 to x of, let's say, 4t cubed plus 7 dt. And we called this g of x. Well, then g prime of x, so the derivative of that whole thing on the left, is just our function inside here, but with an x in it. So it would be 4x cubed plus 7. And essentially, what that is saying, that first part, is really that the derivative and the integral are just undoing each other, essentially. That's why we get the same thing back. And the second part, that's saying if we take our antiderivative, we can sub in our b value and then subtract our antiderivative with our a value. And what that gives us is it'll give us the area under the curve. And now these things are only true if f is continuous on our interval from a to b. So what's wrong with this calculation? You could think of this as x to the negative 2. So if you took the antiderivative, the exponent's going up 1, or took the antiderivative, exponent's up 1, then we're dividing by negative 1, or think of it as 1 over negative 1. So that matches, and then they put the 3 in. Well, 3 to the negative 1 divided by negative 1 is just negative 1/3, and then when you put negative 1 in, that'll give you minus 1, and you get negative 4/3. So all the numbers punched in, but the problem with this is this was never continuous from negative 1 to 3. So although you get a number here, this number does not represent the area under the curve. 1 over x squared looks kind of like that. So if we wanted the area under the curve from negative 1 to 3, well, you can't find that value because it's not continuous there. There's an infinite amount of space you can think of it as there. So you can't actually calculate the area under the curve. So again, the first part of the fundamental theorem of calculus is essentially saying that if you take the integral and then take the derivative, you're right back at where you started, but in terms of x now. And that second part is saying if we take the integral and then sub in our b value minus our a value, we then will get our area under the curve. And that's the one that we're going to use most frequently as a tool. So we'll use that second part in some examples now. Our antiderivative of 2 would just be 2x. and we're going to evaluate it from -3 to 4. So we will get 2 times 4 minus 2 times -3, which will give us 8 plus 6, which will give us 14. In this second example, let's think of this as x to the 1/3, and that will make it a bit easier. We'll take our antiderivative, so our exponent will go up 1 to 4/3. We'll divide by 4/3, which would give us 3/4 out front, and we've got to evaluate it from 1 to 8. So we'll have 3/4 times 8 to the 4/3 minus 3/4 times 1 to the 4/3. And we can neaten this up. Cubed root of 8 is 2. 2 to the 4th is 16. 16 divided by 4 is 4, and then 4 times 3 is 12. So that neatens up all the 12. Anything 1 raised to the 4/3 is just going to come back as 1 always, so we'll just get times 3/4 to give us 12 minus 3/4. So this will give us 11.25, or you could think of it as 45/4. That would be fine as well. Either of those are fine. So next one, we're going to find the exact value of this integral. Secant tan is the derivative of secant. So when we do our antiderivative, we'll just have secant, and we're going to evaluate it from 0 to pi over 4. Pi over 4 is really 45 degrees, which is easier to think about than in radians. So our 45, 45, 90 triangle, we have 1, 1 square root of 2. So we're going to be doing secant of pi over 4 minus secant of 0. So we're doing secant of 45, which is the flip of cos. So we'll have hypotenuse over adjacent. Well, that's square root of 2 over 1, which is just square root of 2. Minus secant of 0, we'll look at our cos curve for this one. Well, cos of 0 is 1. So the reciprocal of that is still just 1. So therefore, we get 1 for secant 0. And then that is the exact value of our integral. And what that's finding our area underneath the curve. Next example, we've got x to the 5/2. So if we go up 1, we'll be at 7/2 now. So we had a 7. If we're dividing by 7/2, we're going to have 2 7s out front. We're going to have x to the 5/2 now. Well, we had a -5, and now we'll have 2/5 also out front. And then we're going to evaluate that from 0 to 4. Well, if we neaten this up, these 7s cancel out, so we have 2x to the 7/2. These 5s cancel out, so we have minus 2x to the 5/2. And we still have to evaluate it from 0 to 4. So if we sub in 4, and because we have 2 parts here, when we sub in 0, we'll want to make sure we put it in parentheses. So square root of 4 is 2. 2 to the 7th is 128, times 2 is 256. Minus, square root of 4 is 2. 2 to the 5th is 32, times 2 is 64. And then minus, all of this will just end up as 0. And don't always just assume that, because you might have, say, like an e to the 0, which is 1, or a cos of 0, which is 1. So it might not always be 0 when you're putting 0 in, so you need to at least think about it. And if we subtract those, we end up getting 192. For our next example, our exponent will go up 1, we'll have 1/3 out front. We'll end up with a minus 3/2 x squared, and we'll have plus 4 to the x, which will be evaluated from 0 to 1. So we'll sub in 1 and sub in 0, so we'll have 1/3 times 1 to the third, minus 3/2 times 1 to the second, plus 4 times 1, minus, and we'll want to start a parenthesis, 1/3 times 0 cubed, minus 3/2 times 0 squared, plus 4 times 0. Well, 1 to the third is 1, times a third is just a third. Similar idea, we'll get negative 3/2 plus 4, minus, all of that will just end up as 0. So our common denominator here would have to be 6. So we'll have 2/6 minus, we'll have 9/6 plus 24/6. And that'll end up giving us 17/6. For our next example, we'll try and neaten this up first before we go any further. This is the same as saying from 1 to 4, x squared minus 1 over x to the 1/2 dx. And what we'll do is we'll divide those each individually by x to the 1/2. Well, this here, this is like saying we have 4 over 2 right now. So if we subtract a half when we divide, we'll have x to the 3 over 2. Minus, we'll just have x to the negative 1/2 and then dx. And this will make it easier taking our antiderivative because we don't have a quotient rule for our antiderivative. So exponent goes up 1 to 5/2, we'll have 2/5 out front. Exponent is going to go up to positive 1/2, so its reciprocal is 2, so we'll have minus 2 out front. And we've got to evaluate that from 1 to 4. So I have 2/5 times 4 to the 5/2, minus 2 times 4 to the 1/2, minus 2/5 times 1 to the 5/2, minus 2 times 1 to the 1/2. And again, anytime it's got more than one part, make sure you're putting it in parentheses after that negative. Square root of 4 is 2. 2 to the 5th is 32. 32 times 2 is 64, so we'll have 64/5. Square root of 4 is 2 times the negative 2 will give us negative 4. And then we'll have negative 2/5 and minus 2. So we're going to need this in fifths. So we'll have 64/5 minus 20/5 minus 2/5 minus 10/5. And actually this should be a plus here because that negative distributed to both. So we should actually have a plus 2 there. And if we combine those like terms where we've really got 64/5 minus 12/5 to give us 52/5. And that's the same as saying 10.4 if you wanted it in decimal form, because it works out nice. So one final example that has a similar kind of simplifying in the beginning. Let's rewrite this as x squared minus x plus 3 over x to the 1/3. So we'll be from negative 2 to negative 1. 2 is really 6/3, so when you subtract 1/3, we'll get x to the 5/3. Minus x is really to the 3/3, so we'll get x to the 2/3. And then we'll have plus 3x to the minus 1/3 dx. Looks like I forgot my dx here. This makes us now ready to take our antiderivative. we'll have x to the 8/3, and then out front we will need 3/8. We'll have x to the 5/3, and out front we will need 3/5, which was negative. And then we'll have x to the 2/3. And then we'll have 3/2 times 3 there, which will actually give us plus 9/2. And we're evaluating that from -2 to -1. So we'll have 3/8, -1 to the 8/3, minus 3/5, -1 to the 5/3, plus 9/2, -1 to the 2/3. Minus, and we'll start a parenthesis, 3/8 times -2 to the 8/3, minus 3/5 times -2 to the 5/3, plus 9/2 times -2 to the 2/3. Cubed root of -1 is -1. To the 8th is +1, times 3/8 is just 3/8. Cubed root of -1 is -1. To the 5th is a -1, times -3/5 would be +3/5. And then we'll get a +1 back when we raise it to the 2/3, so we'll have plus 9/2. Oops, so we got our minus. And then this part's not going to simplify nice at all, because cubed root of -2 is not nice, so we're just going to leave it as is. So 3/8 times -2 to the 8/3, minus 3/5 times -2 to the 5/3, plus 9/2 times -2 to the 2/3. And because that right part's not going to neaten up nice, we could add those fractions together, but it would be perfectly fine to just leave it as is. That is our exact value of the area under the curve. That's all for this video. We'll see you next class period.